Talking next is Erin Gray. Erin is the Senior Geologist at GSWA and she's here to tell you more about our statewide heavy mineral map.
Okay, good afternoon everyone. I'd like to start by acknowledging the Whadjuk people of the Noongar Nation as the traditional custodians of the land on which we gather today. I pay my respects to elders both past and present and extend that respect to Aboriginal and Torres Strait Islanders people in attendance today. So today I will be sharing with you some information about our new heavy mineral project and how this will support critical mineral exploration in Western Australia. I want to talk a little bit about what the project involves and where the samples will come from, the type of analysis we'll be doing to characterise these samples, the planned outputs, and finally focus on the potential applications and impacts of this work. So this project has its origins with and is part of the WA Array passive seismic project. So GSWA were out already digging holes to install seismometers, and we said, why not bring back a soil sample from each of these sites? So this not only leverages the pre-arranged and very comprehensive logistics required for the WA Array project, but also the ground disturbance that is already occurring as part of the rollout of seismometers. So many heavy minerals are resistant to chemical and mechanical weathering, preserving evidence of their host rock characteristics, and thus are useful either for further analysis, such as provenance studies, or simply significant just because they are present, as in the case of indicator minerals. This makes heavy minerals useful in areas dominated by regolith. Looking at the types and distributions of heavy minerals in surface deposits provides clues as to what could lie beneath or in source regions of that material. Also, particular indicator minerals can be evidence for nearby mineralisation. In the context of critical minerals, there are a number of indicator minerals that can vector towards mineralisation associated with those critical minerals, such as columbite and tantalite for lithium, caesium, tantalum, pegmatites. The two main goals of this work are to characterise the heavy minerals in soils from across Western Australia and to detect the presence of indicator minerals for critical mineral systems. I want to take a moment to acknowledge the previous work that has been done in this space. So the Heavy Mineral Map of Australia was recently released, which is a high-quality continent-wide heavy mineral data set that was the result of a collaboration between Geoscience Australia and the John DeLater Centre at Curtin University. If you haven't seen this data set, I would highly recommend exploring it using their mineral network analysis tool. I would like to draw your attention to a sizable section of the map where it says no data. So the majority of the area where there is no data is the northeast half of Western Australia. So as part of this study, we would like to fill that gap, ensuring our data sets are interoperable and consistent with the Heavy Mineral Map of Australia project. As previously mentioned, we are collecting a soil sample from every seismometer site. This means that we're expecting up to 180 samples per phase of the WA array and around 1,485 samples across the 10-year life of the project. These samples will cover multiple geological and tectonic provinces, regolith types and landforms, and will be complementary to the Heavy Mineral Map of Australia dataset, which solely comprised stream sediment samples. The Heavy Mineral Map of Australia dataset also comprised 1,315 samples across the entirety of Australia, compared to our 1,485 just within WA. We'll be using a scanning electron microscope technique called TEMA to characterise the mineralogy of heavy minerals. TEMA is an automated mineralogy technique that uses backscattered electrons and X-ray spectra to identify individual particles and classify them against a library of different reference minerals. TEMA is a fast, efficient and reliable technique, taking around 30 minutes to completely scan a single mount. Here I just want to show some statistics related to the project. So the samples will be collected in a roughly 40 by 40 kilometre grid with 180 samples per phase and 1,485 samples at completion of the project. At the project's end, I estimate that TEMA analysis will have identified over 172 million heavy mineral grains and on average find about 88 minerals per sample. So you can well imagine this is going to generate a lot of data. So what products will we generate with this data? We will create a heavy mineral map of Western Australia, which will involve phased releases of spatial data layers as well as a statewide heavy mineral database. Given the inevitable advancement of machine learning and AI techniques over the next 10 years, the size of this data set means it is a good candidate for the application of current and future techniques. Also appreciating that we will be releasing data from this project for the next 10 years, we're also keeping an open mind as to what data products will be possible or needed in the future. So you'll be hearing more about our Geoscience Data Transformation Program, or GDTP, from Tony Perry this afternoon, but the knowledge graphs currently being developed will underpin these data sets and be critical for delivering future-ready fair data. So this work will have many potential applications. However, three major ones will help to inform about mineralisation potential across the state. The targeted mineral chemistry can unravel cryptic signatures that may indicate that certain minerals have crystallised in mineralising environments, such as the presence of certain trace elements in rutile. This dataset will also be a useful component to integrate into prospectivity maps. I would like to add here as well that while we have solely focused on heavy minerals in this talk, we also have a project that will be analysing the same samples for ultrafine geochemistry, which again is going to be an essential component for future prospectivity maps. Finally, indicator mineral studies, which will involve the detection of indicator minerals such as cassiterite, tantalite, cuprite or garnite, which are associated with specific mineralising systems. In this slide, I just want to demonstrate the capability of this kind of study to detect indicator minerals. This is an example from a recent study that we undertook in collaboration with the John Delata Centre at Curtin University in the West Arunta region of WA. We're currently writing up the results, however, a number of low abundance indicator minerals were detected. So firstly, garnite, a zinc spinel mineral, echondrusite and zinc castorolite were identified, which are indicator minerals for zinc mineralisation, particularly those associated with Broken Hill type deposits. Interestingly, some mineral grains that are not particularly stable in the soil profile were also detected, including cuprite, pyrite, pyrrhotite and pentlandite, which are associated with a range of mineralisation types. A number of cassiterite grains were detected, which can indicate proximity to tin mineralisation. And finally, we also found columbite and tantalite, which, along with cassiterite, may indicate proximity to lithium, caesium, tantalum pegmatites. The main message is that using automated mineralogy, we can find low abundance minerals that may have formed in mineralising environments, and more importantly, those that may suggest we are close to mineralisation associated with those critical minerals needed for the energy transition. Finally, I'd like to finish off discussing what impacts we hope this will have. The end result will be a valuable pre-competitive data set, which will help to reduce the risk of exploration in certain areas of the state, particularly those that are dominated by regolith. With our increasing need to supply critical minerals for the energy transition, such a data set can potentially help explorers to narrow down their search space and reduce the time it takes to make discoveries. Thank you for listening.